A composite function f of x is defined in this manner. F of x equals f of x. This symbol looks like just an open circle. We're going to pronounce that of. So we're just saying f evaluated at g, or f of x. So you've seen this before with just basic function notation. F evaluated at -1, or f of -1. Remember, we simply replace the x with whatever is in parentheses. We're going to do the same thing now, but we're going to use functions rather than just simple numbers. For example, f of x plus h, or f evaluated at x plus h. Everywhere you see an x in the original function, we're simply going to replace that x with whatever's in parentheses, in this case, x plus h. So we have 3x plus 3h plus 2. Now let's let g be 4x, keeping in mind that f is 3x plus 2 from previous. So f of g of x. It might be helpful to rewrite it first. We can think of it as f evaluated at g of x, or again, f of g of x. So everywhere in the original f, you're going to replace that x with what's in parentheses, in this case, g, which is 4x. So we have 3 times replace the x with the g function, plus 2. And simplify. We'll get 12x plus 2. If we're asked to evaluate g of f of x, you can first rewrite it if you want as g of f. That helps us see that the outer function is g, which is 4x. But we're going to replace the x with f, which again is 3x plus 2. And simplify. We get 12x plus 8. If we want to evaluate f of g of -1, there's a couple different ways to do it. One thing we could do first is evaluate g of 1. We know that g of 1 is 4 times -1, because again, g is 4x from earlier. G is 4x. There it is. So we have f of -4 now, and now we can evaluate the f function at -4. And remember, the f function is 3x plus 2. So we replace the x with -4 and add 2. We get -12 plus 2 is -10. An alternate way to do this one is, rather than doing it in 2 parts like that, we already know that f of g is, f of g of x. Earlier we found that to be 12x plus 2. So we can replace that x with the -1 now from the original. F of g of -1 is 12 times -1 plus 2, which is -10. So 2 ways to approach that one. Oh, and I guess this goes down here. We can do a similar process with just a table of values for both f and g. Rather than giving the functions of each of those, if we're given specific coordinates, we can do similar things. So we're given a table for g We're given a table for the f function, and now we want to do the composite f of g. So keep in mind, f of g, we can think of that as f evaluated at the function g. So g is on the inside, f is on the outside. So when x is -2, we've got g of -2 on the inside. G of -2 is 4. So then we're doing f of 4, which is 7. So think of this as f of 4, which is 7. And then x this time is -1. So first we need to do g of -1. G of -1 is 1. And then we're asking, well, what is f of 1? F of 1 looks like it is 4. And we'll just repeat that process. X is 0. So we want to start here. Excuse me. Start here. When x is 0, g is 0. So on the inside, we have f of 0. And then f of 0 is 3. X is 1. So on the g function, when x is 1, g is 1. And then we're looking at f of 1, which is 4. Then x is 2. G of 2 is 4. And then f of 4 is 7. Now we'll do a similar process with functions. We first want to find g of f of x. I think it's best to rewrite it first. Think of this as g of f of x. You don't have to do that, but sometimes it's helpful to see the outer function and the inner function. And the outer function is g, so we have the square root of 1 minus x, but we're going to replace the x with whatever's in the parentheses, in this case, f of x, which we know to be x minus 2. So in parentheses, make sure you put it in parentheses because we will need to distribute that negative sign. And so we have the square root of 3 minus x. And now we can evaluate g of f of 2. Again, if you want, you can rewrite it as g of f of 2. You don't have to, but sometimes it's helpful. Now again, here you have options. You can do it one of two ways. We could first figure out what f of 2 is. So f of 2, if we plug 2 into the f function, we get 0. And now we can evaluate g of 0. Well, g is 1 minus 0. We get square root of 1 is 1. Or we could do it in an alternate way. G of f of 2. We know what g of f is, right? G of f is this piece here. So we could just plug 2 into this function. Square root of 3 minus 2, which is square root of 1, which is 1. Either way, we get the same answer. Since we already have g of f, it's probably quicker to do this one and just use this function. So when we do g of f of 4, we already know the square root of 3 minus x is the formula we're looking for, so we're going to replace that x with 4. And in this case, we get the square root of -1, which is just I. Next, we'll talk about the domain of composite functions. The nice thing about this is we already know how to find domain, so the rules for domain are not going to change. There's just going to be one extra thing we have to be aware of. We want to exclude the values that cause the output of g to be restricted to be the restriction of the outside function, i.e., exclude the x values that cause g to equal the domain restriction of f. Essentially, you want to look at the overall domain restrictions like we've always done, and then look at the domain restrictions of the input function as well. So f of g, again, I like to rewrite it as f of g just to help me see which one is on the inside and which one's on the outside. So f is the outer function, so we have the square root of something minus 1. That f we're replacing with, that x we're replacing with g, which in this case is 2x plus 3. And so we get the square root of 2x plus 2. Now let's find the domain restriction. This is a radical, so the domain restriction is the same as it's been in the past. Remember, we want to take whatever's on the inside and force it to be non-negative. Force it to be greater than or equal to 0. So we subtract 2 and then divide by 2, and we get x is greater than or equal to negative 1. So that's the main part of our domain restriction. But we also need to check for the input function's restriction. In this case, g is the input function, and g is 2x plus 3, which is a polynomial which has no extra restrictions. There's no division by 0, there's no radicals, so we don't have any extra restrictions here. That means our domain is negative 1 included to infinity. Sorry, this actually goes down here. I didn't realize we were doing the next page. Yeah, so our domain we've already found. Here we're looking for f of g. So f of g, again, it might be helpful to rewrite it as f evaluated at g. F is on the outside, so the outer function is 1 over something. We're going to replace that x, that something, with g, which is the square root of x plus 4. And now let's find the domain. So we have the square root of x. We need x plus 4, so we need to make the radicand non-negative, greater than or equal to 0, but then it's in the denominator, so we're going to remove the equality part. Remember, we don't want equality, we want strictly greater than when it's in the denominator. So nothing new there. X has to be greater than negative 4. And now you also need to check the restrictions of the input function. The input function in this case is g of x, the square root of x plus 4, which is the same as what we have here, so there's no extra restrictions. So our domain, negative 4 parentheses, can't include it, negative 4 to infinity. Next, we have g of f. G is on the outside, so the outer function is 1 over something minus 4. Right, we're going to replace that x with the f function, 2 over x plus 1. So the first thing we want to do is simplify this. You typically don't want a complex fraction as your answer. So let's see if we can go through and simplify. And basically you're going to multiply by a funny looking 1. If you look at the denominator of the smaller fraction, that will tell you what we're going to multiply by. You may remember doing this way back in algebra class where you simplify complex fractions. Just multiply by the smaller denominator over itself, and technically you're multiplying by 1, so you're not really changing the value of this original expression, you're just changing what it looks like. So let's multiply. In the numerator, x plus 1. In the denominator, we have x plus 1 times the fraction. Notice the denominator is going to cancel with the x plus 1. You're left with just a 2. Then we need to distribute the negative 4. We get negative 4x minus 4. So we get x plus 1 over negative 2 minus 4x. And this is our composite function g of f. Next, we'll find the domain. This is a rational expression. So just like we've done in the past, you're going to take your denominator and set it equal to 0 and find those domain restrictions. Add 2 to both sides, divide by negative 4, and we get negative 1/2. And remember, that's what x cannot be. X cannot be negative 1/2. But we also have to look at the input function's restriction. So input function in this case was 1 over x minus 4. So the input function in this case is the f function, 2 over x plus 1. And we can look at that and see that negative 1 cannot be there. Negative 1 gives you division by 0, which is a problem. So our interval, everything up to negative 1/2, negative 1. Then we go from negative 1/2, negative 1 to negative 1/2, then negative 1/2 to infinity. And then finally, let's see if we can create the two functions given a composite function. For example, if h is the square root of 1 minus x squared, our goal is to create f and g so that when you compose them, f of g, we get this h function out. So notice g is on the far right, so that means g is the input function. So look on the inside and see what you get. I'm seeing 1 minus x squared, and that means f would have to simply be the square root of x. And so now when you take this g function and plug it into f, we get what h is. Now this is just one example. There's actually more than one way to approach this one. We could also say that g is x squared, and that would make f the square root of 1 minus x. And now when you compose them, f of g, you would plug g into the f, and you get the h function. So this case actually has more than one way to do it. Same thing with the next one with b. There's a couple different ways to do this. You can think of this as the input function being everything inside the bars, and then that would make f just the absolute value of x. So now when you plug in g to the f function, you get the absolute value of 2x squared minus 3, which is h.